Hello everyone, I am Santhi from Department of Mathematics and Statistics, Bhavans Vivekananda College of Science, Humanities and Commerce. In this video lecture, I am going to give Linear Algebra Lesson 3, and in this I am going to introduce vector spaces in linear algebra. This lesson, Vector Spaces 1 of Linear Algebra, has the following two topics. Number 1, Introduction to Vectors in Linear Algebra, and number 2, Vector Space Definition with Basic Examples. So, before defining a vector, let us talk about scalars. What are scalars? In physics or in other sciences, we have learned these things. A quantity that has only magnitude. We call it as a scalar, and we have known scalars. They are all the numbers which come. It can be either natural number or a whole number or an integer or a rational number or a real number or a complex number. Any number which has only its magnitude, we call it as a scalar, and it has only one dimension. And in algebra, and we have the set of all the real numbers which are extended, and all these real numbers are complex numbers, and all these scalars are taken from a field. We call it as f, and here if the scalars are real number, that is a real field, or if we take the scalars are from complex number, that is a complex field. So now all the scalars are taken either from a real field or from a complex field. Now what is a vector? This also earlier you have learned vector as a quantity that has both magnitude and direction. That means basically it has two dimensions only. But when it comes in algebra, our vector is not just restricted only to two dimensions or three dimensions. We have multi-dimensional vectors. For example, let us start with two dimensions. Suppose I take 2, 3. So this is a two tuple, or you can call it as an ordered pair. And we all know like how to represent it geometrically. If you take two-dimensional plane, then you will mark 2 units on the x-axis and 3 units on the y-axis. Then 2, 3 is a point in two-dimensional plane. So in general, I can take a vector v here as like a1, a2, which even I can write it as a column vector, I will call it as. And if these a1 and a2, where are these a1 and a2 are taken from the field? That means here a1, a2 belong to f. So if f is equal to, it can be f can be R, field of real numbers, or it can be C also. So this v is a vector. We call it as it is a vector in either R2 or it is a vector in C2. So similarly, suppose I take an ordered triad, or you call it as 3 tuple 2, 3, 4. How do we identify it graphically, or you can say geometrically? So we can easily understand it is three-dimensional. So we can mark it in three-dimensional space a point which is 2 units, 3 units, 4 units with respect to x, y and z axis. So this is the point we have here. 2, 3, 4. So in general, the same thing I will write here. V is a vector. Suppose a1, a2, a3, and I will even write it as a column vector. A1, a2, a3. Then where are these a1, a2, a3 taken from a field f, where that f is either a field of real numbers or that f is field of complex numbers. Then I'll say this vector v belong to R3, or this v belong to C3. So up to here, 2-dimension, 3-dimension, we can visualize geometrically also. But suppose I take a vector V is equal to A1, A2, A3, A4. Because in algebra, I can have something which can be determined by 4 parameters. Then we cannot visualize it more than 3 dimensions. We cannot visualize, but algebraically we can assume it in abstract way that there are 4 parameters. Then I'll say this is a vector in either R4 or it is in C4. So like this, as we extend, we can even say V is equal to suppose A1, A2 and so on, AN. So I'll get an n-dimensional vector where all these scalars belong to either, as usual, either field of real numbers or complex numbers. Then this V belong to, we'll say Rn or Cn. Right? Now, are these only the vectors? Then even we can have, suppose I take a polynomial, suppose 2 minus 3. It is a polynomial in T. We all know it is a linear polynomial, first degree polynomial in T. Then I can even represent it as a vector 2 minus 3 or 2 minus 3. Now this is also a vector for me. It is a vector in set of all polynomials. So I can generalize it. V is equal to A0 plus A1t. Then this V is even given by vector A1, A2 because in all the polynomials of first degree in T is common. Only the thing that varies are the constants or constant and coefficients. So they are like A0, sorry, A1. This is A0 and A1. So similarly, I take another polynomial. V is equal to like 2t minus 5t square. Then how do I write it this one? So there is no constant, so I'll put in place of constant 0. So this I'll write it as a vector 0 t minus 5. That means I have another vector in the form a0 plus a1t plus a2t square. So this is a0, a1, a2. This is also a vector. So like this in algebra, we can consider so many things as vectors with given parameters. So now we have idea about the vectors, like how are the operations on these vectors. So first I'll take what is vector addition. So we all know these basic operations. Suppose I have, like in matrices, suppose I have 1, 2, a column matrix, another matrix is 5, 6. I know the basic thing how to add this, that is 1 plus 5 and 2 plus 6, which gives me 6 and 8. We call it as component wise addition. So I can say if I have a vector V is equal to, let me say V1 is equal to A1, A2, V2 is equal to B1, B2, then V1 plus V2 is equal to, I can say this as even column vectors A1, A2 plus B1, B2, which is equal to A1 plus A2, A1 plus, sorry, B1 and A2 plus B2, which is again a vector. That means sum of any two vectors is again a vector. Sum of two vectors is again a vector. Now let us see what is scalar multiplication. And we all have this. Suppose I have a vector minus 1, 2, 0, a column, you can say column matrix or column vector, and I take a scalar C is equal to some 2, and this is vector V. Then how do I multiply this 2 and minus 1, 2, 0 This is also a basic operation in matrices we know. We'll multiply this scalar 2 to each element in this column vector. So similarly, if I take CV, so this is nothing but C into the vector V, which will be again a vector. That means a scalar multiplication, if you multiply a vector with a scalar, that will be again a vector. Now we have defined what are vectors and how we are going to add vectors and how are we going to multiply a vector with a scalar. Now let us see what is a vector space. So since we have so many vectors here, suppose if we take a set of vectors, then with the given two operations that are vector addition and scalar multiplication, so how are we going to define a vector space? Let us see the definition here. A vector space is a non-empty set V of objects which are called as vectors. That means you take a non-empty set V which has the objects which we call them as vectors, and on which there are defined two operations, that is called vector addition and scalar multiplication, that what we have defined above, satisfying the following conditions. So we have here a set of vectors V, and it has two different operations, vector additions and scalar multiplication, and then these two have to satisfy, here there are given 10 conditions, all these conditions must be satisfied. So the first condition is u plus v belong to V for all u comma v belong to V. That means if you take any two vectors u and v in this whatever the set of vectors you have taken, then the sum of these two u plus v also should be there in V. That even we call it as a binary, vector addition is a binary operation in V, or you can say vector addition is closed in V. So the second one is u plus v plus w is equal to u plus v plus w. So this is simple associative property for addition, and we know addition is associative on all sets of elements. Whatever you take, whether you take adding to matrices, adding to numbers, or adding to polynomials 2 or 3, like addition is always associative. So you have u plus v plus w is always equal to u plus v plus w. Then what is the third one? There is a zero vector 0 in V such that 0 plus v is equal to v is equal to v plus 0. That means we know zero element, we call it as additive identity. In all the sets starting from the whole numbers, you have zero belong to the sets of numbers, uh, then which satisfy the identity property, that is you add that 0 to any element, it will give you the same result. 0 plus 2 is 2, like 0 plus 10 is 10, 0 minus 2 is minus 2, whatever it is. So the same way this vector space V also should have a zero vector, which, such that if you add it to any vector, it should give you the same vector. Now let us see the fourth condition. For V, each V belong to V, there exists minus V belong to V. That is nothing but negative of any vector. So we all know that if 2 is there, minus 2, 10 is there, minus 10, then minus 100 is there, plus 100 is there. So that if you add them both, it will give you 0. You call it as additive inverse. So the same way in this vector space V also, suppose I have a vector like V, then there should be minus V. For example, if I take a two-dimensional vector like A1, A2 for example, then minus V will be minus A1 minus A2. When you add these two, then V plus minus V, that will give you A1 minus A1, A2 minus A2, which is nothing but 0, 0, 0. So you can say here minus V is the additive inverse of plus V. So in this set of vectors V, there should always be minus V for each V. That is the fourth one. Then fifth one, U plus V is equal to V plus U. This is commutative property for addition, and we know that addition is always commutative on whatever the set of elements you take it. And then let us come for the sixth one. For any scalar C, and vector v belong to v such that we have c into v belong to v. That means multiply this vector v with scalar. That is nothing but scalar multiplication, and we learned earlier that scalar, if you multiply a scalar and a vector, that will give you again a vector. So that itself is the sixth condition here. CV must be there again in the same set V. Then seventh condition, take a scalar C and two vectors u and v, then C into u plus v is equal to Cu plus Cv. It is simply like a distributive property, but distributive property of scalar multiplication over vector addition. Then the eighth one is takes two scalars c plus d and multiply the sum of these two with a vector v. So c plus d into v is equal to cv plus dv. This is also like a distributive property. And the ninth one, c take two scalars c and d and a vector v. C into dv is equal to cd into v, and then for all the scalar. This is also simple multiplication properties. Then the 10th one is 1 into v is equal to v. This is also a known fact. So here 1 is a scalar, not a vector. And then v is any vector. So any vector you multiply with a scalar, then that will give you the same vector v. So any set of vectors satisfying all these 10 conditions, we will call it as a vector space. So v is a vector space. And even we will specifically denote it with V over F. What is this F? It's a field. It is a field. It may be field of real numbers or field of rational numbers or field of complex numbers. Why do you need this field? Because if you want to form a vector, suppose you take V is equal to A1, A2. These scalars A1 and A2 are to be taken from a field. That is why V is a vector space over a field F. This is what the definition of vector space. Now let us see, suppose I take F is equal to R, that is field of real numbers, then V over F will be V over R. We call it as a real vector space. And the same way, if I take V as a C, then, sorry, this is C. Then V over F is equal to V over C, which I call it as complex vector space. Right? Now let us see some basic examples of vector space. So the start with, let me take R2. So we all know it is a set containing the vectors of the form A1, A2 such that A1, A2 belong to R. A1, A2. The scalars are taken from R. So this is even denoted by V2 over R. So over the field of real numbers. So this should satisfy automatically all these 10 conditions what we are giving in this definition, sum of two vectors. So you can say that these type of two vectors, if you add this a1, a2 and one more vector, you take b1, b2, then add them. So their sum is again, it will be there in R2. So simple addition of this any two vectors will always be a vector, the first condition. And the second one, addition is associated with always true for all the additions. So we don't need to bother about that. And specifically I say here, addition is always associated with the second one as well as the commutative. So addition is always associative and commutative. So vector addition, you need not check for that again and again. And then what is the here I can say there are 10 conditions, but what we have to keenly prove the ones one are this one, first one, and the 0 vector one and the negative one, and the scalar multiplication. All the remaining, let me say these are the ones, like, and all these last four also, they will be automatically most of the times be satisfied. So here in this R2, now let me see here. So I can say first one, two vectors, if you take, I explained that how v1 plus v2 will be again in R2, and vector addition first condition is done. And the second condition also will be, that is associative property. Associative property, which is like V1 plus V2 plus V3 is equal to V1 plus V2 plus V3. I'm not proving, just giving you the explanation how will it be. And then the let me take the third one. I can take 0 vector. What will be 0 vector? So the third one, let me say 0. I can say this is 0, 0. So it will be there in V, and you can say 0 plus V is always V plus 0 is equal to V. And the fourth one, I have, if I take V is equal to A1, A2, then minus V will be minus A1, minus A2, then V plus minus V will be 0, 0. So for each V, there will be minus V in this vector space R2, in this set of vectors R2. So this is the additive inverse. And then the remaining scalar multiplication, the fifth one. So this also earlier we explained C into A1, A2, that is CA1, CA2 will be obviously there in V. So CV belong to V, that is scalar multiplication is also satisfied in this. V means here we have R2. So this is R2. This is satisfied, and the remaining, there are 5 more, like all those also will be satisfied. You need not check, because these are all the basic things. It is like a column matrix, and this will satisfy all the conditions. So I can say here R2 or V2 over R is a vector space. Similarly, I can say C2 or C2, I can say this is C2, I'll call it as V2 over C is also a vector space. So in the same way, I can go through the next one, that is R3. This is having the vectors A1, A2, A3, such that A1, A2, A3 belong to R. This is also a vector space. So, and even this is denoted by V3 over R. Similarly, C3, or I can say V3 over C is also a vector space, and so on. Let me say Rn. What is Rn here? So it has vectors of the form A1, A2 and so on An, such that A1, A2 and so on An belong to R. This I will say this is Vn over R is also a vector space. Similarly, Cn, let me write Cn or Vn over C is also a vector space. Now let me talk about another sets of vectors. Suppose I take a set which has, earlier as I explained, that is A0 plus A1t. This is a vector. Even I can write it as A0, A1, again a column vector, such that this A0 and A1 belong to real numbers. They are real numbers. Then this set we call it as P1. This will be also a vector space, because we know that a sum of two polynomials, every polynomial you can convert it as a column vector, and it goes like R2 only, and this will also form a vector space, and we call it as vector space of all polynomials of degree 1. So similarly, what will be P2? This will be vector space of all polynomials of degree 2. So this is also a vector space of all polynomials of degree 2, and then and so on. I can say Pn, which is a vector space of all polynomials of degree n. This will be also a vector space. Like this, we have defined a vector space, and we have seen some basic examples of vector space. In the next lessons, we will go further.